Welcome to Cosmic Calendar, one day of the universe. Here the entire history unfolds in a single day, where every second carries billions of years of meaning. If this is your first time here, remember this. When we look at the cosmos, we are not just observing space. We are reading our own origin story, written in light, time, and physics. Here's a thought that unsettles even scientists. Time itself had a beginning. There was a moment when the universe did not merely look different, but when before had no meaning at all. This video begins exactly there, at the edge where intuition breaks and science must speak carefully. In this first day of our cosmic journey, you will not hear myths or comforting explanations. You will hear what science can truly say about the universe, the cosmos, and the conditions that made Earth life and humanity possible. What we don't know will be respected. What we do know will be explored deeply. If you've ever wondered how the history of Earth, geological eras, extreme events, and even life itself is, connect to the first instant of the universe. You're in the right place. This channel is built for those who want understanding, not shortcuts. So here's the bold idea that guides this series. The universe does not need meaning given to it. Meaning emerges when understanding grows, and that understanding begins with asking the hardest questions, even when the answers are incomplete. If this kind of journey resonates with you, take a moment to engage. Like the video, share your thoughts, and subscribe to Cosmic Calendar, one day of the universe. Each day we move forward together through the universe's story, one carefully measured step at a time. The question sounds simple, yet it bends the mind the moment we sit with it. Before the Big Bang feels like a place we should be able to point to, a chapter missing from a book. But science pauses here, not out of ignorance but out of honesty. Time itself is part of the universe, woven into the fabric of the cosmos, not something standing outside it with a clock in hand. In modern cosmology, time begins with the Big Bang alongside space, energy, and the laws that govern the universe. Asking what came before is like asking what lies north of the North Pole. The question carries meaning in language but not in physics, because time is not a background stage. It is a consequence of the universe itself. General relativity shows us that time stretches, slows, and bends under the influence of mass and energy. When we trace the history of Earth backward through geological eras, extreme events, and the emergence of life, we eventually reach a boundary where equations stop working. At that boundary, time collapses into a single origin. This is not a failure of imagination. It is a boundary of measurement. Science does not invent stories beyond what evidence can support. It marks the edge carefully, acknowledging what is known and what remains unknown, preserving clarity instead of comfort. Some theoretical frameworks, such as quantum gravity, attempt to describe conditions near this origin. Others explore models where the universe may emerge from prior states, but none of these ideas currently provide testable proof. In science, without evidence, possibility remains possibility, not conclusion. When we say the universe began, we are not describing an explosion in space. Space itself was expanding. There was no empty container waiting to be filled. The universe did not appear somewhere. It appeared as everything, including the rules that allow cause and effect to exist. This realization subtly reshapes how we see humanity and our planet. Earth, life, and every chapter of the history of Earth are not accidents floating in an ancient void. They are outcomes of physical laws that began at the same moment time itself was born. And here lies a quiet lesson science offers without preaching. Understanding the universe requires accepting limits with discipline. The cosmos does not rush to explain itself. It reveals only what can be known, inviting us to explore with patience rather than certainty. At the very first fraction of a second, the universe existed in a state so extreme that our familiar laws of physics had not yet taken shape. Temperatures were unimaginably high, densities beyond comparison, and the cosmos was compressed into conditions no laboratory could ever recreate. This was not yet a universe we would recognize, but a threshold where reality itself was being defined. Scientists call this earliest phase the Planck epoch, a span so brief it escapes direct measurement. During this instant, gravity, space, and time were inseparable in ways current science cannot fully describe. Our equations stop here not because the universe becomes mystical, but because our tools are still incomplete. What matters is not what we cannot calculate, but what emerges immediately after. As the universe expanded even slightly, the fundamental forces began to separate. Gravity took on its own role, allowing the cosmos to move from pure intensity into structure. Order did not replace chaos, it grew out of it. This moment laid the groundwork for everything that followed. Without this initial expansion, there would be no stars, no planets, no Earth, and no history of life. Every geological era, every extreme event, every supervolcano in Earth's deep past depends on this first transition from unity to diversity. It's tempting to imagine this beginning as violent, but violence is a human metaphor. In physical terms, it was transformation. Energy shifted form, space gained dimension, and time began to flow forward, setting the arrow that would shape the entire universe. The cosmos did not choose complexity. Complexity emerged because the conditions allowed it. From these early rules, matter would later assemble, collapse, ignite, and recycle itself across billions of years. The universe was not designed with outcomes in mind, yet outcomes were inevitable. When we look at the planet today, at life and humanity, we are witnessing echoes of that first instant. The atoms in Earth's crust, the chemistry of life, and the forces driving extreme events all trace back to this moment when physics itself stabilized. Science teaches us something subtle here. The universe did not start complete. It started capable. And from that capability, everything meaningful was allowed to unfold one step at a time. Almost immediately after its birth, the universe entered a phase that defies everyday intuition. Space did not simply expand. It expanded at an extraordinary rate, faster than light could travel through it. This brief episode, known as cosmic inflation, reshaped the universe before particles, atoms, or light could even form. During inflation, tiny quantum fluctuations were stretched across vast distances. What began as microscopic variations became the seeds of structure. Without this process, the universe would be wildly uneven, collapsing in some regions and empty in others. This balance between uniformity and variation is crucial. Too smooth and nothing would ever gather. Too chaotic and nothing would last. Inflation provided the conditions for matter to later clump together, setting the stage for stars, planets, and eventually Earth within the broader history of the universe. Although inflation lasted for only a fraction of a second, its consequences are written across the cosmos. The large-scale structure of the universe, the distribution of galaxies, and the faint patterns observed in cosmic background radiation all point back to this early expansion. Science does not observe inflation directly, but it detects its fingerprints. Precision measurements align with predictions made decades ago, reinforcing the idea that this rapid expansion is not speculation, but a powerful explanatory framework grounded in evidence. What makes inflation remarkable is not just its speed, but its restraint. The universe did not tear itself apart. It expanded just enough to become vast, stable, and capable of complexity. From this controlled acceleration, the long journey toward life and geological eras became possible. As the universe cooled and inflation ended, energy transformed into particles. The cosmos transitioned from pure expansion into a slower, structured growth. This shift allowed physics to operate in recognizable ways, opening the door to the processes that would later shape planets and extreme events. Inflation reminds us that scale matters in science. A moment too small to imagine determined outcomes too large to grasp. From that fleeting expansion came a universe capable of history, memory, and meaning. As expansion continued, the universe began to cool, and cooling changed everything. Energy that once dominated reality started to settle into more stable forms. The cosmos was no longer an undifferentiated sea of intensity, but a place where distinct particles could exist, interact, and persist. In these early moments, matter and antimatter emerged together, nearly perfectly balanced. When they met, they annihilated each other in flashes of energy. Yet a small asymmetry remained. For reasons still under investigation, matter slightly outnumbered antimatter. This allowed the universe to keep something rather than return to pure radiation. This imbalance, subtle as it was, determined the fate of the universe. Without it, there would be no atoms, no planets, no Earth, and no life. Every geological era, every extreme event in Earth's deep past, rests on this early survival of matter. As temperatures dropped further, quarks combined into protons and neutrons. These particles became the building blocks of atomic nuclei. The universe was beginning to assemble the raw materials that would one day shape stars, supervolcanoes, and our planet. For hundreds of thousands of years, the cosmos remained opaque. filled with a hot plasma of charged particles and light trapped together. Photons could not travel freely. The universe existed in a glowing fog, expanding and cooling, waiting for a critical transition. That transition would eventually allow light to move independently, revealing the first visible imprint of the universe's early structure. But even before light could travel, the rules of chemistry and physics were being quietly established. From this period onward, the universe became predictable enough to be studied, yet flexible enough to evolve. Order emerged without intention, guided entirely by physical laws acting on cooling energy. Science shows us here that creation is not a single moment, but a sequence. The universe did not arrive finished. It unfolded step by step, laying foundations long before anyone could witness them. After hundreds of thousands of years of expansion and cooling, the universe reached a critical threshold. Temperatures dropped enough for electrons to bind with protons, forming the first neutral atoms. This simple change transformed everything. For the first time, light was no longer trapped by charged particles. As photons decoupled from matter, the universe became transparent. Light could finally travel freely across space, carrying with it a snapshot of the early cosmos. This ancient radiation still exists today, stretched and cooled by expansion, offering scientists a direct window into the universe's infancy. This moment did not introduce new drama or sudden violence. It was quiet, almost gentle, yet it marked one of the most important transitions in cosmic history. Without transparency, the universe would remain unknowable, hidden behind its own energy. The patterns within this ancient light reveal subtle variations in density. These variations were not flaws, they were opportunities. Slightly denser regions would begin to attract more matter, slowly growing under the influence of gravity. Structure was no longer just possible, it was inevitable. From these faint irregularities, vast cosmic networks would form over billions of years. Galaxies, clusters, and filaments all trace their origins to this delicate imprint. The universe was now carrying the blueprint for complexity within its own glow. This era connects directly to everything that follows: the formation of stars, the evolution of planets, and the long path toward Earth and life depend on the information encoded in this early light. Even the future geological eras of our planet rest on this distant beginning. Science treats this evidence with care because it is measurable, repeatable, and consistent. The universe left us a message, not in words, but in radiation, preserved across time and space. Here we see a powerful truth of the cosmos. Revelation does not always arrive loudly. Sometimes understanding emerges the moment the universe simply allows itself to be seen. As gravity continued its slow work, some collapsing clouds reached a critical point. Temperatures at their cores climbed high enough for nuclear fusion to ignite. In that instant, the first stars were born, ending the long cosmic darkness. They introduced light not as a remnant but as a source. These early stars were unlike those we see today. They were massive, short-lived. Composed almost entirely of hydrogen and helium, their brilliance was intense. Their lifespans brief, but their impact was permanent. For the first time, the universe began to manufacture new elements. Inside these stellar cores, fusion transformed simple atoms into heavier ones. Carbon, oxygen, and other essential elements were forged through extreme pressure and heat. Without these first stars, the chemistry required for planets, Earth, and life would never exist. When these stars exhausted their fuel, many ended in powerful explosions. These events scattered newly formed elements across space, enriching the surrounding cosmos. The universe was no longer chemically simple. It was evolving, becoming capable of greater complexity. This stellar cycle marked a turning point. Light now came from within the universe itself. Energy was being generated, distributed, and recycled, setting the rhythm for cosmic evolution. Every later structure depends on this phase. Galaxies form around generations of stars, and planets emerge from the material stars leave behind. Even the conditions that allow extreme events on Earth trace their origins to stellar processes that began here. Science reveals that creation in the universe is inseparable from destruction. The death of stars is not an ending, but a transition that enables new beginnings. Complexity is built through cycles, not permanence. From these first lights onward, the cosmos gained memory. Each generation of stars carried forward the results of the last, quietly advancing the universe toward richer possibilities. As generations of stars formed and faded, gravity continued weaving matter into larger, more stable systems. Vast collections of stars, gas, and dark matter assembled into galaxies, becoming long-lasting structures within the expanding universe. These were not isolated accidents, but natural outcomes of earlier cosmic conditions. Galaxies emerged in many forms, shaped by rotation, collisions, and gravity's persistent pull. Some grew into elegant spirals, others into massive ellipticals, while smaller irregular systems drifted and merged. The universe was no longer just forming objects, it was organizing them into communities. Within galaxies, star formation became cyclical. Clouds collapsed, stars ignited, and remnants enriched their surroundings. This ongoing process slowly increased chemical complexity, allowing heavier elements to accumulate over billions of years. Each generation carried more potential than the last. These stellar neighborhoods became the cradles of future planetary systems. Without galaxies providing stability and material, planets like Earth could not exist. The long history of Earth, its geological eras, and the eventual rise of life all depend on these galactic environments. Galactic interactions also played a crucial role. Collisions and mergers reshaped structures, triggering waves of star formation. These extreme cosmic events were not destructive in the long term. They accelerated evolution on a grand scale. Science reveals that galaxies are dynamic, not static. They breathe, grow, collide, and adapt over cosmic time. Their changing forms reflect the ongoing balance between expansion and gravity throughout the universe. Within this framework, the cosmos gained rhythm. Star birth and death followed patterns, creating predictable cycles. Order was no longer temporary, it was sustained. Galaxies remind us that structure in the universe is earned through time. From simple beginnings, vast systems emerged, quietly preparing the conditions necessary for planets, chemistry, and eventually humanity. As galaxies matured, the chemistry of the universe grew richer with each stellar generation. Stars acted as cosmic furnaces, steadily converting simple elements into heavier ones through fusion. With every cycle of birth and death, the universe expanded its chemical vocabulary. Supernova explosions played a decisive role in this transformation. In these extreme events, temperatures and pressures became so intense that elements heavier than iron could form. Gold, uranium, and many others were created in moments of stellar catastrophe, then dispersed into space. These elements did not remain abstract products of distant explosions. They mixed into interstellar clouds, becoming part of future stars and planetary systems. The universe was quietly preparing the materials needed for solid worlds and complex chemistry. Without this enrichment, planets like Earth could never form. Rocks, oceans, atmospheres, and the chemistry of life all depend on elements forged in ancient stars. The history of Earth is inseparable from these long-forgotten stellar deaths. Over billions of years, this process repeated countless times. Each new generation of stars began with more complexity than the last. The cosmos was not rushing forward, but accumulating possibility through repetition. Science shows that complexity does not appear suddenly. It emerges gradually, layer by layer, driven by physical laws operating consistently across time and space. The universe builds patiently, never skipping steps. These heavy elements also made extreme planetary events possible. Supervolcanoes, tectonic activity, and magnetic fields all rely on the internal composition of planets shaped by stellar chemistry. Here the universe reveals a quiet principle. Nothing complex appears without a long history behind it. Every detail of the planet we inhabit carries the memory of stars that lived and died long before Earth existed. As galaxies continued to evolve, stars began forming with surrounding disks of gas and dust. These rotating disks were not random debris. They were structured environments where gravity, motion, and chemistry interacted. Over millions of years, these interactions quietly assembled planetary systems. Within these disks, particles collided and stuck together, growing from microscopic grains into solid bodies. Through countless interactions, these fragments became planetesimals, then protoplanets. This process was slow, uneven, and shaped by both stability and disruption. Not every system produced planets like Earth. Many worlds formed too close to their stars, others too far. Some were torn apart by gravitational interactions. Planet formation was not guaranteed, but it was common enough to reshape how we understand the universe. As planets took shape, their internal heat, composition, and orbital paths set the stage for future evolution. The ingredients created in ancient stars now organized themselves into worlds capable of geology, atmospheres, and long-term change. These early planetary systems were dynamic and often violent. Collisions, migrations, and extreme events were part of their growth. Yet from this turbulence, stable orbits eventually emerged, allowing planets to persist over billions of years. The story of Earth follows this same pattern. Its geological eras, tectonic activity, and internal structure reflect the outcomes of early planetary formation governed by universal laws. Our planet is not an exception, but an expression of a common cosmic process. Science shows that planets are not passive byproducts of stars. They are active systems shaped by physics, chemistry, and time. Their diversity across the universe speaks to the flexibility of natural processes rather than chance alone. In this chapter, the universe demonstrates a remarkable balance. From chaos, order arises not by intention, but through consistency. Planetary systems are the quiet proof that complexity can stabilize when conditions allow it. As planetary systems settled into long-term stability, certain worlds found themselves in narrow ranges, where conditions could persist rather than collapse. Distance from the star, planetary mass, and atmospheric composition began to matter in decisive ways. These factors did not guarantee life, but they allowed chemistry to remain active over deep time. On such planets, energy flows became balanced. Too much heat would strip atmospheres away, while too little would freeze chemical processes into silence. Stability did not mean stillness. It meant the ability to change without breaking, a critical requirement for long-term evolution. Liquid water emerged as a central factor, not because it creates life by itself, but because it enables complex chemistry to unfold. Water acts as a solvent, a transporter, and a stabilizer, allowing molecules to interact, combine, and reorganize. Without it, complexity struggles to gain momentum. Earth fits within this narrow window, shaped by early impacts, internal heat, and a protective magnetic field. Its geological eras reflect a long dialogue between internal forces and external conditions, where balance was repeatedly disrupted and restored through extreme events. Asteroid impacts, volcanic activity, and atmospheric shifts were not failures of stability. They were part of a dynamic system, learning to regulate itself. Each disruption reshaped the planet, creating new paths rather than erasing progress. Science emphasizes that habitability is not a single moment, but a sustained condition. It depends on feedback loops that moderate extremes, allowing chemistry to persist across millions and billions of years. Stability emerges from interaction, not isolation. Across the universe, many planets may briefly pass through such windows. Few may remain there long enough for complexity to deepen. Time, more than location, becomes the deciding factor in planetary potential. Here the cosmos teaches restraint. Possibility does not demand immediacy. It rewards patience. Worlds capable of lasting change are those that endure long enough for chemistry to explore its options. Long before life appeared, planets like Earth entered a phase where chemistry could experiment without interruption. Simple molecules formed, broke apart, and reassembled in countless ways, driven by energy from sunlight, internal heat, and chemical gradients. Nothing here was alive yet, but everything necessary for life was slowly taking shape. Carbon-based chemistry proved especially flexible. Carbon atoms bonded easily with others, forming complex chains and structures. In oceans, shallow pools, and mineral-rich environments, these molecules interacted repeatedly, increasing in diversity and stability over time. This process was not guided by intention. It followed physical laws acting on matter under specific conditions. The origin of life was not a single event, but a continuum, where chemistry gradually crossed a threshold into self-sustaining systems. Certain molecules began to store information, while others facilitated reactions. When these roles combined within enclosed environments, early systems could persist, repair themselves, and replicate imperfectly. Variation emerged naturally, setting the stage for selection. Earth's geological activity played a crucial role here. Volcanism, tectonics, and hydrothermal systems continuously recycled materials and energy. These extreme events did not hinder chemical progress. They fueled it, creating new environments and opportunities. Science does not yet claim a complete answer to how life began, but it identifies plausible pathways grounded in evidence. Laboratory experiments and planetary studies show that the building blocks of life form readily under realistic conditions. What matters is not the mystery that remains, but the pattern that emerges. Life did not require rare miracles. It required time, stability, and a planet willing to keep changing without collapsing. In this quiet chapter, the universe reveals something profound. Complexity does not need a sudden spark. Given the right conditions, it grows naturally, step by step, until something entirely new becomes possible. Once life crossed the threshold into persistence, time became its greatest ally. Early life forms were simple, microscopic, and limited in scope, yet remarkably resilient. They survived not because they were complex, but because they adapted to whatever the planet offered. Evolution did not rush forward. It advanced through variation and selection. Guided by environmental pressures rather than goals, small changes accumulated across immense spans of time, shaping life slowly, patiently, and irreversibly. Deep time became the canvas on which biology could experiment. Earth's environment was anything but static. Atmospheric composition shifted, oceans changed chemistry. Geological eras unfolded with cycles of stability and disruption. Each change filtered life, favoring some forms while eliminating others, driving diversification without direction. Photosynthesis transformed the planet in ways no organism could foresee. By releasing oxygen, early life altered the atmosphere, reshaped oceans, and triggered new chemical pathways. What began as a survival strategy became a planetary force. This transformation was gradual and often destructive. Oxygen proved toxic to many early organisms, causing widespread extinction. Yet from this crisis emerged new opportunities, allowing more energy-efficient life forms to evolve. Science shows that progress in evolution is inseparable from loss. Complexity does not accumulate smoothly. It advances through thresholds, where old systems fail and new ones emerge, better suited to altered conditions. Every later form of life, including humanity, traces its lineage back to these early experiments. The long history of life on Earth reflects the outcome of countless trials conducted by nature over billions of years. Here, the universe teaches endurance. Change does not reward speed. It rewards persistence, flexibility, and the ability to survive long enough for possibility to mature. Over time, life moved beyond single cells, exploring cooperation and specialization. Multicellular organisms emerged, allowing tasks to be divided and energy to be used more efficiently. This shift did not happen once but multiple times, each experiment testing new ways to survive on a changing planet. As bodies grew more complex, interactions between organisms intensified. Predation, competition, and symbiosis began to influence evolutionary paths. Life was no longer just adapting to the environment, it was actively reshaping it, altering ecosystems and energy flows across Earth. Oceans became dynamic arenas of innovation. New forms appeared, diversified, and vanished as conditions shifted. Geological eras left clear signatures in the fossil record, showing how tightly life and the planet were linked through time. The atmosphere continued to evolve alongside biology. Oxygen levels fluctuated, climates shifted, and feedback loops emerged between life and geology. Earth was no longer a passive stage. It had become a responsive system influenced by living processes. Extreme events played a decisive role in this acceleration. Volcanic activity, climate swings, and mass extinctions periodically reset ecosystems. These disruptions did not erase progress. They redirected it, opening space for new forms to arise. Science reveals that complexity thrives under pressure, not comfort. Stable periods allow refinement, while crises force innovation. Life's history is shaped by this tension between continuity and disruption. Each advance increased the planet's biological influence. Life altered soils, oceans, and even the chemistry of rocks. The boundary between biology and geology grew increasingly blurred. In this phase, the universe shows how simple beginnings can lead to transformative outcomes. Given enough time and interaction, life becomes a force capable of reshaping an entire planet. Across immense spans of time, complexity continued to layer upon complexity, eventually giving rise to nervous systems. These systems were capable of sensing, learning, and responding with increasing precision. Intelligence did not appear suddenly. It emerged gradually, shaped by survival pressures and environmental challenges over deep time. On Earth, certain life forms began to model their surroundings internally. Memory, anticipation, and problem-solving offered advantages. These traits were refined across generations, embedding awareness into biology without foresight or intention. The development of brains marked a turning point. Energy-intensive and fragile, they persisted because their benefits outweighed their costs. Perception expanded beyond immediate reaction, allowing organisms to plan, cooperate, and adapt with greater flexibility. Humanity represents one outcome of this long process, not its destination. Our species carries the accumulated results of billions of years of evolution, shaped by geological eras and climate shifts. Extreme events filtered survival again and again. With intelligence came the ability to reflect on origins. For the first time, the universe produced a form of life, capable of studying the cosmos, reconstructing Earth's history, and asking how the universe began. Awareness turned outward, toward the stars that made it possible. Science reveals that intelligence is not separate from nature. It is an extension of it. The same laws that governed particles after the Big Bang govern thought, curiosity, and understanding within human minds. This moment does not elevate humanity above the universe. It situates humanity within it. Consciousness becomes a process through which the cosmos examines itself, using the same physical rules that shaped galaxies and life. Here the universe reaches a subtle threshold. From energy and expansion arose matter, from matter arose life, and from life arose understanding. The journey did not aim for awareness, but awareness emerged all the same. Today the universe is still expanding, still evolving, still unfolding its long story. Galaxies drift farther apart, stars are born and die, and planets continue their quiet revolutions. The cosmos has not reached an end state. It remains dynamic, governed by the same laws set in place at its beginning. Earth occupies a brief moment within this vast timeline. The geological eras that shape the planet are chapters in a much longer narrative, one that stretches back to the first instant of time itself. Humanity exists within a narrow window, balanced between deep past and uncertain future. Science allows us to reconstruct this journey with remarkable precision. Through observation, measurement, and theory, we trace connections from the earliest moments of the universe to life on this planet. Knowledge becomes a bridge across time, linking origin and presence. Extreme events have not ceased. Supervolcanoes, climate shifts, and cosmic impacts remain part of the universe's ongoing behavior. Stability is temporary, not permanent. What endures is change itself, operating within consistent physical rules. In understanding this, perspective shifts. Humanity is neither central nor insignificant. We are participants in a process far larger than ourselves, shaped by forces that existed long before and will persist long after. The universe does not pause for reflection, yet reflection arises within it. Through science, the cosmos becomes interpretable, its patterns revealed without losing their depth or scale. Understanding grows even as mystery remains. This moment invites awareness rather than conclusion. The story of the universe is not finished, and neither is our ability to explore it. Each discovery refines how we see our place within the whole. Standing here at the edge of cosmic time, we are not outside the universe looking in. We are the universe, briefly conscious, tracing its own history through reason and curiosity. Understanding the beginning of the universe is not about memorizing facts or timelines. It is about learning how reality behaves when pushed to its limits. When we follow science back to the first moments of time, we are not just studying the cosmos. We are training our minds to respect evidence, uncertainty, and scale. What you can take from this journey is perspective. The history of Earth, its geological eras, life, extreme events, and even humanity itself, are chapters in a story that began long before our planet existed. Seeing that connection changes how knowledge is valued and how questions are asked. So let me leave you with a few questions to carry forward. If time itself had a beginning, how does that reshape the way we think about origins? If the universe follows laws without intention, where does responsibility emerge within intelligent life? And if we are brief witnesses in a vast cosmic process, what kind of curiosity do we choose to cultivate? If this exploration helped you see the universe with clearer eyes, consider becoming part of this journey. Subscribe to Cosmic Calendar, One Day of the Universe, and activate notifications so you don't miss the next day in our unfolding cosmic timeline. Each episode builds carefully on the last. Carl Sagan once reminded us that we are a way for the cosmos to know itself. Science does not diminish wonder, it deepens it. The more we understand the universe, the more meaningful our place within it becomes.